get to it, I guess. It's Friday. Hopefully the stream is live. I should check the other computer. So in my class yesterday, we had our first spam bot. Yeah, it was. I've finally gotten to the point where spam bots actually think that they can do something with my channel. So, yes, the first one was offering to a website to sell me like followers and stuff. So no, of course not. Maybe, yeah. Um, huh? Yeah, except I haven't monetized the channel, so because there's sort of like the obvious ethics problem there. Yeah, I don't know. Maybe I'd make enough money that I wouldn't care about ethics anymore. Uh, who knows? Um, all right. Well, let's get to it then. So, first off, let's make sure that the audio is good. Yeah, looks like we're good there. Uh, all right. So, I wanted to kind of talk to finish with the floating point stuff. Um, which to do that, let's see. I wanted to pull up. Um, let's see, where did I put it here? Files done. Dropbox. Come on. Oh, all right. Let's do it that way. Okay, all right. Let's see. We want to go to files. Wabash. Teaching. Oops. CSC101. Spring from 20, I think is where I've got this. Notes. Floating point. Okay. Um, oops, that's not what I wanted. So let's look briefly at my notes here. So this goes through basically most of the floating point stuff that we've already talked about with some examples. But what I wanted to talk about is um, the some of the special encodings. Okay, so in the IEEE 754 standard, um, it there are a couple of exceptional encodings. Okay, where they look funny and you wouldn't, I think, normally interpret. Let me see if I can open this in. Uh, excuse me. Um, see if I can open this in something a little bit better. Why does it not? Let's see. Export. Yeah, whatever. I don't feel like messing with this. Okay, so there are a couple of sort of oddities in the floating point standard. Okay, one of them is actually the number zero. Okay, which if we were to look at, so what I mean, what do you think the number zero would be encoded as? How about all zeros, right? What else would it be? Um, well, but in a sense, that's sort of an exceptional encoding because if we took the, well, okay, so the sign bit would be a zero, that's no shock. The mantissa would be four zeros, and the exponent would be three zeros. If we interpreted that as in the usual way, then that would be 1.4 zeros times 2 to the something. Okay, well, if the exponent field's all zeros, it looks like 0, but what does it count as? Hmm? Well, minus in this direction, yeah. Hmm? No, it'd be uh, -3 if it's all zeros, right? Because what's the exponent bias? 3, okay. And so the exponents look 3 bigger than they are. Well, okay, sorry, let me rephrase. What is the exponent bias in 8-bit floating point? It's 3, right? In 16 or 32-bit, it's different, but uh, in 8-bit floating point, it's 3. Okay, so if we had the exponent that looked like it was 0, okay, namely all zeros, when you factor in the bias, it counts as -3. Okay, so if you saw the 8-bit number all zeros and you didn't know that that was special, you would interpret it as 1.4 zeros times 2 to the -3. Okay, so let me go over to the notes and the scribble thing and write this down. Okay, so special encodings. Okay, so if you had this, you might interpret it as 1.0000. Okay, how do I know it's all zeros there? Because that's the mantissa field. Okay, and then times 2 to the exponent. What's the exponent here? The exponent looks like 0, right? Because it's all zeros. But in fact, it's that. Okay, so you might interpret it this way. Okay, and what is 1 times 2 to the -3rd? Well, whatever, right? Let's see, it'd be half, an eighth, a 16th, half, a quarter, an eighth. Yeah, okay. Um, so fine, whatever. Um, but this, okay, so let's see, how do I want to say this? Um, that's not how we actually decode this particular bit pattern, okay, for in float 8. So if you just blindly went into it, you might say, oh, well, that's gonna just take it like any other bit pattern, okay? But what this one encodes is actually, and it would help if I could write this morning. Um, it actually encodes the number 0. Okay. And would you guys agree that there ought to be an encoding for the number 0 because, well, you do some arithmetic, maybe the answer is going to come out to be 0. Okay, so we need to have an encoding for that as a floating point number. And what would be a logical choice? Well, what was 0 encoded as when we were working in the integer land? All zeros. So this would certainly be a natural thing to pick as our encoding of 0 is just all zeros, okay? But it is technically an exception to the rules for floating point, okay? Because we might think that we should interpret it as 1 times 2 to the -3rd, but that's not how we're going to interpret it. Yeah. Okay, good question. So Cole's question was, what happens when you need 1 times 2 to the -3rd? Um, in 8 bits, you can't do it. Um, No, it wouldn't wreck the computer. It's more so that you just can't represent what you want on the computer. So the computer has sort of I mean, computer arithmetic, right? Everything is there are only finitely many numbers that it can understand or represent. And, um, well, okay, so there is another answer to that question, which is you can't do 1 times 2 to the minus third in 8-bit floating point. But nobody actually uses 8-bit floating point for real arithmetic, right? Uh, at bare minimum, people use 16-bit, and for real floating point stuff, it's either 32 or 64-bit nowadays. I mean, even back in the 80s, right? When I think it was 1984 or so when this particular standard started to kind of coalesce. Um, Single precision, so sort of the base floating point standard, really was defined around a 32-bit float number. Okay, 32 bits. Um, and in certain contexts, you can get away with half the precision of that, and that's what it's called, half precision, as a 16-bit floating point number. Um, the 16-bit floating point is actually used some in computer graphics, where it's sort of close enough. So great. Um, and it's faster to compute because, well, you're only dealing with half the bits. But for any actual floating point stuff, people are using 32 or even 64 bits. I mean, like I said, I think last time, how many bits does NASA use for its computations? It's using 64-bit floating point for sending space probes to other planets, right? So if that's good enough to get all the way from here to Pluto and be, well, okay. I don't know, how many of you guys think Pluto's a planet? How many of you think Pluto's not a planet? Yeah, yeah. You're a Pluto's not a planet kind of guy? Get out. No. Yeah, that's fine. So does the International Astronomical Union or whatever it's called. But yeah, so if we can get a space probe from here to Pluto accurately with 64-bit floating point, then that's pretty good, right? Like, do we really need to go any more precise than that? And for most practical purposes, 32 bits probably enough. Um, I mean, unless you're NASA. Okay, um, so the moral of the story is nobody actually uses 8-bit floating point to do anything except teach, right? So the only reason that we're using 8-bit floating point is because it's simple enough to write down, and it doesn't take, half the page, but that's basically it. Okay, so is that okay? All right, so what about if I took this number and I threw the sign bit as a 1, left everything else all zeros, but I made the sign bit a 1? How might you interpret that? If all zeros is 0, then what do you think 1 followed by 7 zeros would be? 0, but it's got a negative sign bit, so what might you think that is? Negative 0? Well, what does that mean? Well, yeah, not really, right? Because 0 is neither positive nor negative. So, um, but on the machines, we actually deliberately defined this thing called negative 0. So let me go back to my thing here. Okay. Um, the reason that that's a good idea is that it allows us to define things like, well, what do you think 1 divided by positive 0 should be? Like, I mean, does it, in a mathematical sense, does it make sense to divide by 0? No. Okay. But if you were to think about, like, what's 1 divided by a really tiny positive number? It's like, what's 1 divided by point, bunch of zeros, and then a 1? it's going to be some really big number, right? Okay, so for how many of you guys, by the way, have taken or are taking some sort of calculus class, right? Okay, so you think about limits, right, in the context of calculus. So when you divide by a really tiny number, you get a really gigantic number. Okay, so what should have in a limit kind of context, what would be 1 divided by 0, or let me rephrase, 1 divided by positive 0? How about plus infinity? Okay, would that be a useful thing to have sort of programmed into your machine or built into your machine? Yeah. Okay, and this then explains why it's useful to always also have the idea of minus 0, because what would 1 divided by minus 0 be? Negative infinity. Okay, so do you see the utility of having that as sort of a special case? And the representations for those are um, if you have uh, if you make the exponents all ones and the mantissas all zeros, then that allows us to use these encodings to represent plus or minus infinity, okay, which is useful, right? Or at least I think it is. This, by the way, is what would make it like if you were building a calculator. If you divide, let's say you do 1 divided by 0 on your pocket calculator, what's it going to do? Yeah, it'll probably say undefined or error or something like that. But how does it know to display the word error or undefined or whatever? Well, it knows to do that because the encoding of the result from the floating point unit is, you know, the thing for plus infinity or minus infinity. And so it's going to say, oh, I just got plus infinity as an answer, or this bit pattern really is an answer. I'll display error to the user in that specific situation. Okay. Um, right. Now, um, there's two other sort of exceptions. So we've talked about plus and minus 0, okay? Also then therefore plus and minus infinity, okay? There are two other kind of weird encodings which are encode the concept of not a number, okay? So this might seem a little bit weird to think about, well, why would you need something separate for not a number if you've already got something for plus infinity? But here's a good reason for that. So what's the square root of -1? Yeah, we call it an imaginary number, right? Well, that's not plus and minus infinity, is it? It's a different concept, okay? So if you were building like a calculator or something and it has a square root button on it, then it might be the case that the user says, okay, I want to do the square root of a negative or a logarithm of a negative or something like that, okay? Where the answer is, um, well, in a mathematical context, you would say an imaginary, okay? But um, in a computer context, that doesn't make sense. Well, at least to the computer, okay? Excuse me, goodness. So, um, by having a different encoding stand for not a number, then that enables us to sort of differentiate between the situation where we might have plus infinity versus uh, the situation where somebody asked what the square root of -1 is, or the logarithm of a negative, or something like that. Okay, so we have a different encoding for those situations, and there are sort of two categories of them: quiet, not a number, and signaling, not a number. And for the quiet versus signaling is not really important for our purposes, but um, but we've at least got that encoding. Okay, so the situation where your exponent field is all ones is where then we reserve those and interpret them as not a number situations. Okay. Um, Now that does mean that we have reduced the number of genuine floating point numbers that we can represent. Okay, because we've reserved some of the encodings to stand for special things, not what we think that they mean. And in 8 bits, where you have such limited precision to begin with, that may seem like a really bad idea. But, again, think about then doing this in 32 bits, where you're going to have quite a bit of precision, so it's not really a big deal to spend a couple of special encodings on infinity or not a number kind of situations. Okay, so is that all right? Um, yeah. So there are some exceptions. Basically, is the moral of the story here. Um, um, and actually, let me show you guys this because it's kind of interesting. Um, so here's my source for that NASA uses 64-bit floating point. Right. So here's JPL. How many decimals of pi do we really need? And somewhere in here, it says that basically, let's see, where is it? Yeah, if you go 5 to, or sorry, pi to 15 decimal points, then if you make a circle, that's, from here to the Voyager space probe in radius, then your circumference calculation would be off by an inch and a half if you used only 15 decimal points. All right, seems like it's probably good enough then. Uh, and that happens to correspond to exactly a 64-bit floating point number. They don't explicitly say that here, but if we go back to our float toy thing, 15 decimal points is 64 bits worth of floating point numbers. So if it's good enough for NASA, it's probably good enough for us, I would hope. Okay. All right. So, any other floating point is just kind of starting to sink in. Hopefully, yeah. Take a little bit of practice, but yeah. Okay. So the sort of next sort of encoding lesson is, well, like, what are we looking at here? We're looking at a bunch of text. Okay. How is that encoded? Yeah. Okay. Yeah, exactly. Okay, each letter is going to be assigned a specific numerical value that goes with it. Okay, and when we do that, I don't mean like hexadecimal, right? So the letter A as a hexadecimal character represents a particular 4-bit pattern, right? But the letter A as a textual object is going to be a different pattern. So the original standard for this, so let's just open up here. Um, okay, it's called Ascii. And so let me pull up a table here for this. Okay, so here's an Ascii table, and I've got a nicer looking one that I'll put on Canvas as kind of a reference. So the original ASCII standard was a 7-bit standard. It very quickly got extended to be an 8-bit standard. Okay. How many things can you encode with 8 bits? 256. Okay. So, and 7 bits would be therefore 128. Okay. So, these will represent the encoding in hexadecimal or decimal, understanding that that's really an 8-bit pattern, okay? And the standard is there's a lot of special characters at the beginning. So like, for example, all zeros is called a null terminator. That's important because it's a way to signal that you're at the end of a textual object. And then there's all this special stuff. So for example, like acknowledge, inquiry, bell, backspace, right? A lot of these things are um, useful for if you're transmitting data back and forth. You can say, have one computer tell another, like, yes, I got the message, or no, I didn't get the message, or something like that. Okay. Um, so those aren't printing characters, but they're defined in ASCII anyway. The ones that we care about for actually typing things then would be all the like letters and symbols and stuff. Okay, so in uh, with 8 bits, we can only encode 256 things. Okay, and we spend a bunch of them on these sort of special, like transmission encodings. Okay, fine, whatever. But then we get to spend the majority of them on text. All right, so you got 256 things worth of encoding. Well, how many letters are there in the English alphabet? 26. Really 52 because we've got capitals versus lowercase, and those need to be encoded separately. Okay. We also have 10 digits, 0 through 9, and then we've got a bunch of punctuation marks and other sort of special symbols like, the $ or percent or whatever, right? Okay, so each one of those spends an encoding. All right, so if we can do um, all of the letters, okay, and punctuation marks and digits and kind of other special symbols, um, like that should be good enough, right? Got the whole alphabet here. Well, what about if you're Chinese? Then what's the problem? How many symbols are there in Chinese? Thousands. Okay. And that's just Chinese, right? So the problem, or a problem with ASCII, is that it's very American centric, right, and English centric, in the sense that like we can encode everything we could possibly want in English with a 7-bit ASCII standard. But there's a lot more that we would like to encode than just English, okay? So very quickly it got extended, and here's the other half, the sort of second half of it, um, to be, well, okay, you guys, a lot of you studied Spanish in high school probably, or maybe French, anybody? Oui? Ah, français, très bien. So in French or Spanish, right, you've got Latin letters, like in French, for example, you've got the E with an accent on it, okay? Or the C with a little dangly bit called the cedilla. And in French, that tells you the difference between a hard C like cat versus a soft C like city, okay? Um, well, if you don't have an encoding for that, it's just going to look like the letter C with no dangly bit, okay? So in Western European languages, there are Latin letters with extra decoration that mean things. Okay, right? So, right in Spanish, you've got the N with the tilde above it for distinguishing between like here's a good one, right? What's the difference between anos and años in Spanish? Huh? Anybody? And that's exactly what it means, right? It's the difference between year and butthole. So, right, that's an important letter or important thing to be able to encode is the N with the tilde on it, right? So, uh, yeah. So, so the second half of the ASCII table using the 8th bit gets you another 128 characters, and that allows you to encode all of the different symbols or all the different sort of Latin letters with decorations on them. Okay, from Western European languages like Spanish or French or whatever. Okay. And then we also can start to define, therefore, some but not all of the Greek letters and some mathematical symbols like plus and minus. Okay, that's kind of useful, or less than or equal to, right? If you're trying to type a mathematical expression, having that on in your palette of available characters is useful. Okay. Um, and then there's a bunch of other things. They look like garbage, right? Like these things, but they're actually, I mean, you guys are maybe a little young for this, but how many of you like used a computer back in the day that only had like DOS on it, not Windows, just old school DOS? Well, exactly. You're too young, right? Because was anybody born before the year 2000? Okay. And if you were, it was barely, right? So you were starting to use a computer maybe like 2004, 5, roughly. Clippy? Oh, wow. Yeah. Does anybody remember Clippy? Yeah. Who was Clippy? Yeah, it looks like you're writing a letter. Would you like to form? Yeah. So Clippy was one of the little assistants that was built into one of the, well, it was before Windows XP, uh, but a version of Microsoft Word or Office, right, where it would be like, you'd type like "Dear Sir," and then Clippy would pop up, and it'd be like, "It looks like you're writing a letter. Would you like me to format it like it's a letter?" And it was this little paperclip looking thing with eyeballs, because yes. In fact, let's find a picture of Clippy. Huh? Yeah, but he kind of got a bad rap. Um, yeah. So there's Clippy, right? I mean, he's kind of a handsome guy, right? He's even got the little eyelashes, right? No, I mean, the graphics quality is not super high because, of course, this was a while ago. You could get other assistants, but this was the default one. Was Clippy. Um, yeah. Uh, anyway. Um, yeah. I kind of miss Clippy. Um, so anyway, um, why did we bring up Clippy? Oh, yeah, yeah, old school computer stuff. Okay. Where were we? I wanted the ASCII table. Where was that? Here. Okay. So, uh, in before we had graphical user interfaces, you needed basically a way to make an interface. And so some of these funky looking things, if you put them together, you can make like boxes or things like that to make sort of a really cheesy looking graphical interface. So that's what a bunch of those ones that look like garbage are. But then we've also got our some but not all of the Greek letters, um, and mathematical symbols. So like here, I know it's a little hard to see. Is the top and the bottom half of an integral symbol from calculus. Okay, you've got, less than or equal to. You've got this thing here, which is sort of an upside down U, is important in set theory, and uh, the particular Greek letters that are represented are the ones that are basically like used in mathematics, okay? But not all of them are there. And that's just Greek. I mean, that's European even, right? So what do you do if you're Chinese? You're kind of hosed, right? Or at least with ASCII, you're hosed. You can't represent all of the thousands of different characters that are in Chinese, and that's just Chinese. What about if you want to do Korean or Japanese or well, okay, yeah, true, but point being, you still need to encode those, right? Uh, or Russian, or I mean, Chinese is I think the best example here because it has thousands of different symbols. Okay, so this ain't gonna cut it if that's what you're trying to do. So then what? What do we do if we want to encode Chinese? Yeah. Or it's built in, right? So one way would be to type in using Latin letters to represent Chinese sounds, okay? Which is like there's several different ways to do this, like pinyin or whatever, okay? But that doesn't like really solve the problem, okay? So the um, the solution is called Unicode. Okay, so if 8 bits can only encode 256 things, and we want to encode thousands of things, what's the only solution? Is we have to spend more bits on encoding. Okay, fine. But how do we assign which letter, or sorry, which number is associated with a particular Chinese symbol? Well, we better agree upon that sort of thing in advance. Okay, and Unicode is the standard for this. Okay, so let's go to the Unicode code charts. And um, you can use, I mean, I think Unicode by default, you're using 32 bits. Okay, how many things can you encode with 32 bits? It's like four point whatever billion. Okay, that's a lot of symbols, right? We're probably not going to run out of that anytime soon. Okay, so at least if we want to represent anything reasonable. Okay, so what all is in here? Well, um, I don't know about you guys, but I really find myself very frequently needing to type ancient Egyptian hieroglyphs. Yeah, I mean, it's something I do every day, don't you guys? Yeah, and it's in Unicode. Okay, that's great, right? We can represent as a number uh, an ancient Greek or sorry, ancient Egyptian symbol. Okay, why not, right? So let's look at ancient Egyptian stuff here in the code chart. This might take a minute to load. Uh, here it is. Here we go. Right? Wouldn't it be useful to be able to type these things? I mean, if you're an archaeologist, it certainly would be. Okay. Yeah, cool. Yeah, okay, this is a good point. Um, yes and no. Okay, so this is the difference between encoding and a font, right? So let's say that you type a paper in Word, right? And each letter is being encoded in either ASCII or Unicode, one of the two. That encoding is different than the font that you put on top of it. Okay. So a font determines how the character looks on the screen or paper. The encoding just is which number are you attaching to each symbol. But how it looks is a totally other problem. Yeah, it's going to have these pixels here, and right. So that's a font kind of issue, but that's separate from the encoding issue. Okay, and maybe a good a good. I mean, you guys have all used different fonts, right? It's the same text, just it looks different because you're layering that on top. Um, so I mean, here we've got our ancient Egyptian symbols, right, which may seem kind of absurd. But what other kind of symbols like this do you guys use probably genuinely on a daily basis? Hmm. You use emoji. Those are all defined in Unicode, and a separate number is associated with each emoji. But how the emoji is displayed is another matter. Okay, so how many of you guys are iPhone people? Okay, how many of you guys are Android people? Get out. Um, so if I make the gun emoji in huh? Well, you can, but what does it look like on an Apple device? Looks like a little squirt gun, right? What does it look like on Android? Yeah, just like a little pistol, like a real pistol, right? Well, it's the same Unicode character. It's just that it looks like a squirt gun on Apple or a real gun on an Android device. Okay, now maybe that's kind of a silly example, but another one would be how do you the emoji for cheeseburger, right? What does that look like? Well, yeah, it looks like really you don't say. Well, yeah, I know, right? Fair point. Okay, but and this is sort of this is important. Okay, I don't know how many of you guys who puts the cheese under the patty. Like what is wrong with you people? Huh? Yeah, yeah, exactly, right? So, right, Apple, Google. I mean, look, Google. What is wrong with them? They put the cheese under the patty. This is just unacceptable. Huh? I guess, right? But it's a hamburger, right? Like seriously? Okay, and I would disagree too with Apple because who puts the lettuce on the bottom? No, it should be bun, patty, cheese, then the lettuce, then the tomato. Microsoft, yeah, um, yeah. Okay, so I don't know who these heathens are who are and what kind of crazy hamburgers they eat in California, but uh, I mean this is just unacceptable, right? Um, but okay, all of the, I mean, yeah, it may seem silly we're sitting here talking about emoji, uh, but each emoji is a separate Unicode character, right? For hamburger, squirt gun, the poop emoji. Actually, you guys know the ice cream cone, right? The ice cream that's on the ice cream cone is actually the same as the poop emoji. It's just different color. I know, makes you really kind of gross, right? Uh, yeah. So we got all these stupid emoji. I mean, if we've got 4 billion characters that we can encode, we might as burn some on poop emojis and hamburgers, right? I mean, uh, yeah. Okay. So, but all of that's encoded as in Unicode, and a bunch of the emoji, right, started to get added in basically the last 10 years. Um, now, here's where I get to utilize my authority as a professor, the guy running the class. What else might you want to encode? I mean, we got hamburgers and guns and whatever else. I don't know about you guys, but I really need to be able to type in Klingon on a daily basis. And Klingon is not part of Unicode. The consortium that runs it, they rejected the application from the Klingon Language Institute to add code block dedicated to Klingon. Huh? Yeah. But now we have poop emojis. Yes, I know, right? Um, and 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 Klingon's not like Chinese, right? There's only a fixed number of characters you need. You don't need thousands of them. Yeah, so we can have hamburgers and poop emojis, but not Klingon. Rip. Okay. Anyway, so point being, though, Unicode allows you to encode textually all manner of different symbols, right? And ancient Egyptian, I mean, if you're an archaeologist, it might be kind of useful to be able to do this. Um, and there's all kinds of other stuff in there, right? So if you speak Russian, okay, or any of the other Eastern European languages that use the Cyrillic alphabet, you know, some of them are regular Latin letters, but most of them aren't, right? You've got the like, um, you know, the backwards N. Where is it? Huh? Yeah, row five. Oh, oh, that's hilarious. Yeah. Okay. Somebody did that on purpose. I bet you, right? Just because, yeah, they're like he he he. Um, all right, but like the backwards N, or like the backwards in with a symbol above it, or you know, any of that stuff, right? If you want to be able to type Russian or any of the other, you know, kind of Eastern European Slavic languages, you need these symbols, okay? And there you go, you got all of them, capital, lowercase, etc. Um, and okay, wonderful. And then let's take the say the Chinese ones, right? Of course, there are thousands of those. So let me just load. Let me just load one piece of it just for sake of demonstration, right? I don't know Chinese, so I don't know what any of these things mean. But um, is anybody taking Chinese? Call. Wow, actually, that's a lot. Normally, when I teach a class, I have like one person who's in Chinese. All right, so which Chinese class are you guys in? Cole, I know you're in 101. All of you in 101? Okay, all right. Well, so you know, you may not know what any of these symbols mean yet, but right, uh there are thousands of them, and they all have their associated bit pattern in Unicode. Um, but then we've also got, you know, the ridiculous ones like the emoji. But then there's all kinds of other languages that you might want to be able to represent for, you know, archaeological purposes. Like, well, we looked at the ancient Egyptian. Um, there's also, well, here's one like linear B, right? So these are kind of like old. You'd find these in like um, some of the Egyptian, I mean, not Egyptian, but islands in the Mediterranean from sort of pre-Greek civilization. And, you know, if you're an archaeologist, you'd want to be able to represent these things. Um, you know, what they mean is sort of a completely other matter. Um, or like, say, cuneiform, right? How many of you guys have read Gilgamesh? Right, those of you who are not freshmen, because you haven't gotten there yet, although you probably should have read Gilgamesh before you got here, right? Cuneiform, right? Useful to be able to represent that stuff. Okay, so um, and to sort of finish, right? That's not a font issue. How it looks on the screen is a font problem. How it gets encoded in text is either going to be done in ASCII or Unicode. For just regular English stuff, you can get away with ASCII. But if you want to do anything exotic, uh, like French even, you've got to either use extended ASCII, which adds the 8th bit in and gets you another 128 characters, or do everything in Unicode. Now, the nice thing is that everything that's ASCII is also valid Unicode. Okay, so it's sort of a backwards compatible standard. That's useful. Okay. All right, so we'll talk about this a little bit more at the beginning on Monday, and otherwise, have a fantastic weekend.